Hey everyone, welcome back and let's solve some Leetcode today. So today we are solving Leetcode 1539, Kth Missing Positive Integer. We are given an array of positive integers that are sorted in increasing order. Our work is to find the Kth missing integer from this array. You can see here from example number 1, we have the array 2, 3, 4, 7, 11, and k is 5. So we are supposed to find the fifth missing integer. And clearly here you can see the missing integer is number 9. Similarly to example number 2, the missing integer is number 6. Now, all of these instructions are simple, but how can we do this? How is it possible to find the missing value in this array? Well, your first thought might be to use a hash set or a hash map or an array to keep track of all the missing positive integers in the input array. And basically that would work. Definitely it will work. However, its time complexity is O of n, and this operation requires O of n extra space for the hash map or the array that will be used to store all the missing values. Now this is a very efficient algorithm, but then if you look closer into the question, you find that there is a follow-up that asks you if you can do this in a time complexity that is less than O of n. Is that possible? Is there a better solution? Well, definitely there is. Now, this one is quite tricky to come up with because you might not notice, but this problem requires you to understand binary search for you to solve it. For every array that is sorted in ascending order, the value at any point in the array is represented by its index plus 1. So in this example, you can see for the first value, which is 2, its index is 0. In a normal array that is sorted, we will start from 0 going all through to n. So in this case, it will be 0, 1, 2, 3, 4, and 5. Now at position 0 in the array, that will represent the value number 1 if all these integers are positive and in ascending order. At position 1, the value will be 2. And at position n minus 1, the actual value will be n. So that is very clear from a normal array that is in ascending order. Whenever we have the index of a value in any sorted array, we should be able to determine how many numbers are missing from it. From the example that we have here, you can see from index 0, the current value that we see now is 2 instead of 1. Therefore, this means that there are 2 minus 1 values missing from the array. This must mean that there are 2 minus 1 values missing from the array. That is 2 minus 1, which is 1. And it is clear that we have already skipped the value 1 and went straight ahead to 2, but it is placed at index 0, the position that should be holding the value 1. So therefore, when we're given the index of an array and the value that is stored there, assuming this array is organized in an increasing manner and it only contains positive integers, we can assume that there are missing values if the value that is there does not correspond to this formula that I'm showing. If it does not conform to this formula, then there must mean that there are some values which are missing. Now, with that in mind, we can employ a binary search solution to find the kth missing integer from this array. The explanation for this is quite simple. One, we need to find the number of missing positive integers at any given point. This will be represented by the midpoint value, which we should compute in a binary search. Once we have the midpoint, this will represent the number of missing integer values at that given point. If the number of missing positive integers at this midpoint is lower than the kth value, we will continue our search to the right of the midpoint. Otherwise, we will search to the left of our midpoint, and I will show you this right now. Once we find a value that is at least kth, we can return our left index. Now, this left index represents the left index in the binary search plus the kth value. because 1, this left pointer will have crossed with our right pointer at this point. This is basically a while true loop that we will be implementing. And so once the left pointer intersects or overlaps with the right pointer, we have to stop our binary search. And at this point, we will have found the number of values that we have already skipped, or rather the number of positive integers that we have already skipped. This will indicate how many steps far from k we have already gone. Now, in addition to this, we will have found the number of steps that we need to go backwards in order to get the kth value if we add it from the kth pointer. So the solution that we will return in this case will be the left index plus the value of k. The good thing with this solution is that its time complexity is n log of n, which is much more efficient as opposed to O of n. It's clear that we are dividing the problem into two every time in the loop, and we are just searching in one half of the array to find the values that represent the kth value. Now let's code this up. So the first base case that we need to consider is that 1, if the value of k is ever going to be less than the first value in our array, then we just need to return this value at the first point. Otherwise, we will be doing our normal binary search. So in a normal binary search, you have your left and right pointers, and the left pointer will start from 0. The right pointer, however, will start from the end of the array. So we can get the end of the array by just doing the length minus 1. And we will be doing this while the left pointer and the right pointer have yet to intersect. So we'll be doing this while left is less than or equal to right, because the left pointer must be to the left of this array, and the right pointer must be to the right of this array. We will compute our midpoint. This is quite simple. You can do it in many ways, but in Python, the best or the easiest way is to take the left plus the right and then divide that by 2. Notice that here we are doing integer division and not decimal division. Now, remember the formula that we were doing. We are checking that the current value in our array, which is the value at the midpoint, subtracted by the midpoint value plus 1 is less than k. Now, if this ever evaluates to true, if this formula ever evaluates to true, so if this ever evaluates to true, we need to update our left pointer and we'll be shifting it to the mid value plus 1. Otherwise, we'll be shifting our right value to the midpoint minus 1. Now, once this evaluates, once these two pointers have intersected, then it means that our left pointer will be at a position whereby we have moved k steps further from the value that we are looking for. So what we just need to return is the left pointer plus k, and that should be our solution. Now let's run this and see how efficient it is. And as you can see, it's pretty efficient. If you like this video, like and subscribe, and I will see you in the next one.